Welcome to this video lecture on structural analysis. In this lecture we will discuss about moment distribution method and we will also solve one example and we'll see how these steps can be applied. First of all, the general principles. What are the steps involved in this moment distribution method? This moment distribution method is a displacement method of analysis for solving indeterminate structures, and it was developed by Professor Hardy Cross in 1930. It is a method of successive approximations that may be carried out to any desired degree of accuracy. The method begins by assuming each joint of a structure as a fixed, whether it is roller support or pin support. We will consider the joints as fixed. Determine fixed end moments for each member of the structure from the table of fixed end moments. Then we determine stiffness factor and distribution factor for these members. Then we go to the next step, which is the main step of moment distribution method, where we unlock those fixed joints which are not fixed, and then later on we will lock these joints in successive steps, and then the internal moments at these joints will be distributed, so that unbalanced moment will be distributed into the members which are connected at that joint. Here you can see with this example, if we take this beam, it has two members AB and BC. Joint A is fixed, joint C is fixed, but B is not fixed, it is roller support or rocker support. So what we have to do in the beginning, we will consider joint B as fixed for our calculation purpose or for applying our moment distribution method for this problem. So when we make it fixed, there will be fixed end moments at B and C also. At A there will be no fixed end moment because there is no load. So we will calculate these fixed end moment for this loading condition when there is UDL on the whole span, and we can find these values from the table of fixed end moments, which I have calculated here as 8000 and 8000 at C. Then in the next step, when we go for unlocking, we release this joint and allow it to come to the equilibrium position. That's why if you see here, the moment is in the anti-clockwise direction. So when we remove this lock, the moment will try to come into equilibrium by applying a moment in the opposite direction. So that's why its moment will be 0 and the joint will come into equilibrium. This is the main procedure, and we'll continue this process until all the joints are balanced. Here are some of these definitions which we have to learn, because we have to use these quantities for calculations. Member stiffness factor will be calculated, which is defined as a factor at an end of the beam that can be defined as amount of moment required to rotate that end by an amount of 1 radian. If you look at this beam, here is support A, which is roller support, and B is fixed support. If we try to rotate this end A by an angle of theta when the far end is fixed, so here this is the point which we are considering. We are trying to rotate this end, so this will be considered as near end, and the other end, which is B in this case, will be considered as far end. In this case it is fixed. So moment required for rotation of joint A comes out to be 4 EI theta A by L. When we put this theta A equal to 1, this gives you stiffness, and this will be equal to 4 EI by L, which we can say KAB, where A is the near end and B is the far end. So first suffix is near end, B is the far end. Similarly, if we look at this case, when the far end is pinned, the member stiffness is taken as 3EI by L, which will be, in this case, if we calculate for KBA, so B will be the end which we are considering and A will be the far end. This will be taken as 3EI by L. In some cases you will find that modulus of elasticity is same for the whole material. So in that case those common values will be cancelled and we can calculate this relative stiffness factor, which will be just I upon L if all the ends are considered as fixed. We also have to find the joint stiffness factor. If there is a joint and at this joint there are many members connected, then summation of all the stiffness factors for the members which are connected at A will give you the joint stiffness factor. As in this case, if you look here, stiffness for AD, stiffness for AB, stiffness of AC is given, for example, then the total stiffness or the joint stiffness for A will be calculated as the sum of these three stiffnesses. This will be required to find our distribution factor at a joint. Then we have to calculate distribution factor for each joint. The fraction of total resisting moment supplied by the member is called the distribution factor. How much moment will be going to that branch or that member, that will be decided by this distribution factor, which is equal to the stiffness of the member divided by the joint stiffness. And the important thing is carryover factor. When we apply a moment here at near end A to rotate this end by theta A, half of that moment will be induced at the far end, which you can see here in this equation. Moment MAB is 4EI theta A by L, whereas the moment which is induced at the far end will be 2EI theta A by L. So we can say that half of that moment will be induced on the far end. If we apply a moment of 10 kilonewton meter at A, then 5 kilonewton meter will be induced at the far end, which is B. So this ratio is known as carryover factor, which is 0.5. Now we will try to solve one example and you will see how these steps are applied to solve indeterminate structures by using this moment distribution method. So here we have a beam which has these two parts, the same beam which I have shown you earlier. So you have to use moment distribution method and find final end moments and draw SFD and BMD for this beam. So first step will be that we will keep this joint B as fixed, and then based on that we will calculate the values of our stiffness factors, distribution factors, fixed end moments, and then we will go for applying all the steps. First step is to find these stiffness factors KBA. So we will substitute the values. The formula is 4EI by L. I is given in this question, so we substitute by this numbers. L is 3. Then we calculate KBC 4EI by L again, so we got these values. Then distribution factors for BA, in the same way it will be stiffness for BA divided by the joint stiffness. So at B there are two members, BA and BC, so we have to put here stiffness of BA and stiffness of BC in the denominator. So this way we can get these values. For distribution factor for BA 0.4, distribution factor for BC is 0.6. Now when we come to the fixed ends at A and C, distribution factor for AB will be taken as 0 because here we have a fixed support, and on the other side this is, so fixed support will have very infinite stiffness. So when we substitute here, this whole thing will become 0. Similarly here at joint C. So remember that at the fixed end the distribution factor will be 0. Nothing will be distributed. Then we calculate fixed end moments. For fixed end moment we have to use the table for fixed end moment, which will be available in your textbook, or also if you get the question in the exam, the data sheet will provide you the table of fixed end moments. Here we have to define the sign convention. Clockwise moments will be taken as positive and anti-clockwise as negative. When we go to this step here, as I mentioned earlier, that joint B will be considered as fixed. So this is a portion of your beam AB which has both ends fixed, but there is no load. So moment, fixed end moment AB will be 0, fixed end moment BA will be 0. When there will be any load, you can calculate depending upon that loading. Now we come to this part, BC. BC is like this case, so I have selected from that table of fixed end moments. So at B there will be a moment of WL square by 12, but it will be in the anti-clockwise direction, and at C it will be in the clockwise direction, WL square by 12. But according to our sign convention, I have taken here as minus WL square by 12. The value of W is this load UDL substituted here, and fixed end moment for CB is 8000 kilonewton meter. Now we go to the main step for balancing the joints or distributing the unbalanced moment, because this moment is extra moment which has induced because of this fixed support. So we have to balance this joint. So the fixed end moment at B then holds span BC in this fixed or locked position. To correct this, we will apply an equal but opposite moment of 8000 Newton meter to the joint and allow the joint to rotate freely. So when we release, it will come to its equilibrium position. That means it will rotate in an opposite direction. If the moment here is 8000, so in other words we can say that we have to apply a moment of 8000 Newton meter to bring it to equilibrium position, which is shown here in this diagram. As a result, the portions of this moment are distributed in spans BC and BA, because there are two parts at joint B. If you look on the left hand side, there is BA, on the right hand side we have BC, and these 8000 Newton meter will be distributed according to the distribution factors of these spans BA and BC. So moment which will be transferred to BA will be 0.4, which is distribution factor of BA multiplied by the unbalanced moment 8000. This comes out to be 3200 Newton meter, and moment in BC is distribution factor of BC multiplied by this unbalanced moment, which comes out to be 4800 Newton meter. These moments must be carried over, since the moments are developed at the far ends of the span. So that carryover moment will be transferred to those far ends, whereas the carryover factor is 0.5. So from BA, half of that moment will go to AB, and from BC, half of the moment will go to CB, which is written here. So moment carried over to AB will be 0.5, carryover factor multiplied by the moment of BA, this is 1600, and similarly the moment carried over to CB will be 2400. Now after this, if we see that there is no unbalanced moment, so we can say that all the joints are balanced, and we can stop at this stage, and at the end find the resultant moments at each joint. All these steps of moment distribution are usually presented in a tabular form, and you can see here we can put these values in a nice way in tabular form. You can see here we prepare this table: joint A, B and C. Which member is connected at A? There is one member AB which is connected at A. We write these values, which are the members connected. At B there is BA and BC. At C we have only one member, CB. Then we substitute the values of distribution factors which we have calculated in the previous steps. Fixed end moments which we have calculated, we will just write here. Distribution fact of the moments, unbalanced moment. Now if you look here at B, there are two members, BA and BC. So in this case, in BA the moment was 0, in BC the moment is minus 8000. So we can say that this joint is not balanced, it is not in equilibrium. So to balance this joint we have to apply plus 8000 Newton meter. Now that 8000 Newton meter will be distributed into these two branches, which is BA and BC. So 8000 multiplied by BA comes here, 8000 multiplied by 0.6, the distribution factor for BC will come here. Then after distribution we'll go to the step of carryover. So from BA half of that moment will go to AB, and from BC half the moment will go to CB, that is 2400. At the end we have to take the algebraic sum of all these moments, starting from fixed end moment, distribution, carryover, and then finally this value. So it is 1600. Here for BA 3200, and the algebraic sum for BC is minus 3200. Now you can see here BA plus 3200 and BC minus 3200. That means the algebraic sum of these two will be equal to 0. So we can say that the total moment at B is 0. Then at CB this is 10,400. Now we calculate the support reactions at these supports. For that we will consider each span separately, because if you look here, these are the moments, the values you calculated here. So we have these values, so just show these proper directions for these moments. And now we will calculate the reaction by applying equations of equilibrium. First we consider the portion AB, and then we take moment about A, and in that case VB into 3 minus 3200 is this value, and then we have another moment here minus 1600, and this whole thing will be equal to 0. There is no other moment. So from here we can say that VB is equal to 1600 Newton meter in this upward direction. So we get this reaction 1600, because sigma Fy is equal to 0. So for equilibrium the sum of these two should be equal to 0. If VB is in the upward direction, VA will be in the downward direction with the same magnitude. Then we go to the part BC, where we have these moments. Here 3200 Newton in this direction and 10,400 Newton meter in this direction. We are doing the same thing. Sigma MB, take the moment about any point, equal to 0. So VC into 4, we are taking moment at B. Then look at the moments, because of this UDL, which is 6000 Newton per meter multiplied by 4 multiplied by 2, the distance of its center from point B, minus these moments, if you see here. So we consider these moments and then plus these values 3200. In that case we come to this value of VC, which is 13,800. So we have got these reactions. Similarly VA, and so these values will be calculated. This is actually VB, not VA. This is VB equal to 10,200. Now we can easily draw the shear force diagram, because you know the reactions here. So for each portion separately, for AB because the values are known to you. If you see here, this reaction is in the downward direction 900, and there is this is 1600 Newton downward, so the shear force diagram will be just a rectangle, and that gives you this shape, rectangular, up to this point. Then we come to the portion BC. In BC we have these reactions. Here VB is 10,200 and VC is 13,800. So we substitute these values here and draw the shear force diagram. So this is shear force diagram for the portion BC, and this completes shear force diagram in a simple way for this beam ABC. Now we go to bending moment diagram. To plot bending moment diagram, again we will plot the bending moment diagram separately for each part. For this part, if you see, and there are two types of loads. One load is because of the loads applied, and the other is the support moments, which are fixed end moments at the supports. If you see here, we have support moments also. So some moment will come because of the loads. Here in this case there is no load applied, so on span there is no load, but in this case there is a span which this span is having some moment, so because of this there will be bending moment, and bending moment due to these support moments also. So we have to draw diagram for both loading separately, and then we will use principle of superposition to find the resultant bending moment diagram. So here, as there is no load, so it will be just a straight line with zero value. Here we have uniformly distributed load, so this value is WL square by 8, giving you a parabola, and maximum value will be at this center, which comes out to be 32,000. Then we look at the bending moment diagram due to the support reaction. So here at this point the support reaction is there, positive, and at this point the support moment is negative, so we substitute these values here. Similarly here the support moment is negative, so we put here this value, and then we draw the diagram. But here in this case, if you look at this diagram, here you have to look at the direction, how these moments will be applied. We have to look for the concept of sagging and hogging moments. So when we look at this end, the moment applied here, which is in the anti-clockwise direction, this will be hogging moment, and here in the clockwise direction on the right hand side will be hogging moment. So we are taking hogging moments as negative, and sagging moments, which are because of this uniformly distributed load, are taken as positive. So we draw these diagrams separately. This is for the span moments, and this is for fixed end moments, so due to the loading, and this is for fixed end moments. And then finally we can draw the resultant bending moment diagram in a simple way. Just invert this diagram over the bending moment diagram due to the load, and that we can easily see that this value, so positive will come down and negative goes up, as it is just inverted, or you can say the mirror image taken on the positive side. So this is resultant bending moment diagram. In the next lecture I will explain some more examples.